Today I'm going to talk about how to push the repair performance to the limit in erasure-coded storage. So we are now dealing with big data, and we need to store the data in distributed storage systems, which consists of multiple storage nodes or servers. However, as we scale out the storage systems, failures become very common. So it's important to provide the fault tolerance guarantees, including availability, which means that the data should remain accessible even under the failures, and also durability, which means that there's no data loss when the failures happen. Erasure coding is a very promising redundancy technique that can provide these fault tolerance guarantees. And it provably achieves the minimum data redundancy through some encoding operations. And it also provably achieves much higher reliability with the same storage overhead than replications. So erasure coding has been reportedly deployed in enterprises like Google, Azure, and Facebook. For example, Azure reportedly reduces the storage redundancy from 3x used in traditional replication to 1.33x using erasure coding. And that translates to petabytes of savings and also a lot of savings in operational costs. So what is erasure coding? The main idea is the following. Basically, we have two configurable parameters n and k, where k is less than n. The first thing we do is we divide the data into a collection of fixed size pieces, which we call the blocks, and there will be k blocks. And we will encode these k uncoded blocks into n-coded blocks and distribute this set of n-coded blocks to n nodes. We call this set to be a stripe. So in practice, there will be many stripes of blocks distributed across many nodes. And erasure coding has a property that any k of these n blocks could sufficiently rebuild the original file data. So this is an example of nk equals to 4, in which we divide the file into two blocks, and we do the encoding operation to generate two additional coded blocks. And here, the plus operation means the bitwise exclusive OR. So any two of these four nodes can reconstruct the data. On the other hand, if you want to achieve this fault tolerance using replication, you need to store 3 copies of data. So here, I only use 2 times redundancy, while in replication, I need 3 times redundancy. For those of you who are familiar with erasure coding, this code is also called the systematic code, which means that k of these encoded blocks are equivalent to the original k uncoded blocks. So you can access them directly without doing the decoding operations. However, in our work, we don't distinguish between the coded or uncoded blocks. We just collectively call them blocks. And in actual practice, a lot of erasure codes used in modern storage systems satisfy the properties called the linearity and also addition associativity. And we found that actually each of these blocks could be expressed as a linear combinations of any k blocks in the same stripe based on the Galois field arithmetic. For example, I can express any block B as a function of A1, B1 plus A2, B2 up to A4, B4, where here k equals to 4, and AI represents some encoding coefficients, while the blocks B are the blocks in the same stripe. And actually, this is the fundamental idea of resolving codes, regenerating codes, and also the LRC. The 2-letter codes are the newly proposed erasure codes in the literature. And also, these properties also apply to XOR-based erasure codes. So for example, in the example I showed earlier, it is purely based, the encoding operations are purely based on exclusive OR operations, which gives very good computational efficiency, and these properties are also applicable. So the good thing about erasure coding is you can save a lot of storage redundancy while achieving high fault tolerance. However, the bad thing is about the performance bottleneck. And in particular, the repair performance is very poor compared to traditional replications. In general, if I want to use erasure coding, I need to retrieve k blocks in order to repair a failed block that is either lost or unavailable because of failures. So there has been a lot of work in the literature on how to mitigate the repair penalty of erasure coding. so that I can still maintain the benefits of storage efficiency while I can mitigate the performance overhead due to repair operations. There are two lines of work. So one line of work is to propose new erasure codes that can optimally achieve the minimum repair bandwidth, or I/O. For example, the well-known codes are the regenerating codes and LRC and Hitchhiker. So regenerating codes provably achieve the optimal trade-off between the storage efficiency, storage overhead, and also the repair bandwidth. Another line of work is the efficient repair approaches that work for general erasure codes. For example, lazy repair, and also the PPR, which I will introduce in a moment. So let's take a look at why erasure codes has high repair penalty. So we call this the conventional repair scheme. So that applies to the classical erasure codes, such as the Reed-Solomon codes. For example, if I want to repair an unavailable block, which we call the single block repair, so what conventional repair does is to retrieve K blocks from K working nodes. We call these working nodes as helpers. And the block will be repaired and stored at another node called the requester. So this requester could refer to a client who wants to request an unavailable block, or it could be a new node to reconstruct all the blocks in a failed node. So in this case, the requester will collect all these K equals to 4 blocks from 4 helpers. Now, suppose that the time needs to transmit 1 block over a link is 1 time slot. As you can see from here, the bottleneck is on the downlink of the requester. So the total number of time slots that I need to do this conventional repair is K time slots, because I need 1 time slot to transmit 1 block over a link, and the requester needs to download K blocks in total. And the reason for this K time slots is because the bandwidth usage is not quite even. So you can see from this example, the downlink of the requester is overwhelmed, while the links among the helpers are idle. So can we make the bandwidth usage more even? So recently, in the EuroSys 2016, there's a work called partial parallel repair. Basically, it exploits the linearity and addition associativity to perform repair in a divide and conquer manner. So let's take a look at the same examples and see how it works. So in the first time slot, N1 will send N to A1, B1. And because of this linearity and addition associativity, N2 can combine A1, B1 with this locally stored B2 and to form A1, B1 plus A2, B2. Similarly, N3 can send A3, B3 to N4, and N4 can combine the received A3, B3 with A4, B4 to form A3, B3 and A4, B4. And both of these partial operations can be done in the same time slots because the links are not interfere with each other. They are independent, so they can do it simultaneously. Now, in the second time slot, N2 will send the partial result to the N4, and N4 can receive the partial result to form A1, B1 plus up to A4, B4. And finally, in the third time slot, N4 will send to the requester the repaired block. So from this example, if we want to see what is the repair time, that will be reduced to 3 time slots. And in general, given K, the repair time is equal to the ceiling of log 2K plus 1 time slot. So the repair time is reduced from K time slots in conventional repair to log K time slot in this scheme. However, from this example, we still see that the repair time of erasure codings remains larger than the normal read time. If you just read 1 block, you only need 1 time slot. However, when you repair an unavailable block in erasure coding, you need more than 1 time slot. And this observation holds even for those repair optimal erasure codes, such as regenerating codes, because it still needs to read more data than the amount of failed data. So in general, it still needs more than 1 time slot to reconstruct a failed block. So in practice, erasure coding is mainly used for storing the warm or cold data that is less frequently accessed, so that the repair penalty only happens to those data, while for the hot data, it still remains replicated. So here comes the open question: can we reduce the repair time of erasure coding to almost the same as the normal read time? And we believe that that could create the opportunity for storing hot data with erasure coding. One example is to address the tail latency problems. Few papers in recent OSDI and FAST conferences propose to use erasure coding to address the tail latency. So here come our contributions. We propose repair pipelining is a very general technique to speed up the repair performance for general erasure coding. And this repair pipelining could be applicable for two types of repair operations. One is degraded reads, and one is the full nil recovery. And we theoretically showed that it could achieve O1 repair time in homogeneous setting. O1 means that the repair time is independent of the parameters N, K used in erasure coding. So we extend this repair pipelining also to heterogeneous environments, which is commonly found in practice. And we built a prototype EasyPipe and integrate this as a middleware with two open source distributed file systems, HDFS and QFS. And we conduct extensive experiments on a local cluster and Amazon EC2, and we showed that the repair time could be reduced by 90% and 80% over conventional repair and PPR, respectively. So what is repair pipelining? Basically, it has two main goals. The first goal is to eliminate any bottleneck link. So the basic idea is we don't want any link to carry more data than any other link. And at the same time, we also try to effectively utilize the available bandwidth resources during the repair operations so that we make sure that no links are idle while doing the erasure coding, while doing the repair operations. And our key observation is that in actual erasure coding operations, the coding unit, which we call a word, is in fact has a much smaller size than the actual read-write unit, which we call the block. For example, when we do the resolvement codes, the word size can be as small as 1 byte, or maybe just 2 bytes or 4 bytes, depending on the erasure coding operations. While the block size used for the read-write operations will be up to 64 megabytes, because we want to minimize the seek time for the read-write operation. So in general, they will try to make the block size as large as possible. So we can see that actually there's a significant gap between the word and block size. And when we do the erasure coding, actually erasure coding will apply to the words at the same offset to form a stripe. Let me show you an example. So let's say we have n blocks of a stripe. In actual erasure coding operations, each block will be divided into many pieces of words, and we will perform the erasure coding operation for the words at the same offset to form a stripe. So even though we call the n blocks as a stripe, but in fact there are many small stripes for the erasure coding operations. And we leverage this property in our repair pipelining design, which is not used in the previous work in conventional repair and also PPR. So the main idea is very simple. Basically, we just slice a block, and what we mean is we divide the block into multiple slices, each of which could contain multiple words. For example, I can configure the slice size to be 32 kilobytes. And then we pipeline the repair of each slice through a linear path. The slice size could be configurable, which I will show you the trade-off in the experiments. Here, I show you an example how repair pipelining works. So let's say I want to repair a block again, and k equals to 4. So what I would do is I first divide this block into 6 slices. And for each slice, I will form a linear path. So N1 will try to repair the first slice here. So N1 will send to N2 A1, B1. So N2 can combine with A1, B1 with the locally stored data A2, B2, and then send the result A1, B1 plus A2, B2 to A3, N3. And then the helper N3 will combine the received result with the locally stored A3, B3, and send the result again to N4. N4, and then send the final result to requester. Now, while N2 is sending the data to N3, N1 can work on the next slice. So it would also, N1 will compute the results for A1, B1 for the next slice and send to N2, while N2 is sending the data to N3. And we do this in a pipeline manner. Now, the transmission from one helper to another helper is now reduced to 1 over S times log, as opposed to 1 times log in the previous example, because in the previous examples, we transmit 1 block over a link, while in here, I only transmit 1 slice over a link. And if we do some little math, we can show that the repair time is equal to 1 plus k plus 1 over s times loss. And if s is sufficiently large, which is commonly found in practice, it would be approaching 1 times lot. And for those of you familiar with communication networks, this idea is quite similar to wormhole routing, which was proposed in the 90s. So we apply this idea to two types of single failure repair operation. Single failure repair is the most common case in practice according to the field studies. The first example is degraded read, in which we repair an unavailable block at the client, and full node recovery, in which we try to repair all the lost blocks of a failed node. It doesn't have to store the reconstruct blocks at a single node. In fact, it's possible to reconstruct all the lost blocks at multiple nodes. And we can apply a scheme called a greedy scheduling to try to distribute the repair load of multiple stripes across the helpers. Now, one challenge of repair pipelining is that the repair performance could be degraded by the presence of stragglers. And I'd like to point out that this problem is not specific to repair pipelining. In fact, it also the similar problem found in any repair of erasure coding scheme, because it requires to retrieve the data from multiple helpers. So as long as one helper becomes very slow, the overall repair performance could be slowed down. So what we do here is, suppose that we can predict which one is the straggler, and we try to bypass the straggler in our repair pipelining process. And more generally, we try to address the heterogeneous environment. So in heterogeneous environments, we assume that the link bandwidth could be varying and arbitrary. And we address two specific cases. The first case is there's limited bandwidth when a client wants to issue the reads to a remote storage systems. So you can think of the storage systems is on the cloud. It tries to rebuild the data internally inside the cloud, and then we deliver the repair block to the client. And the bandwidth at that point is very limited. So what we do here is we propose a cyclic version of repair pipelining to allow the clients to issue parallel reads from multiple helpers. And in the second case, we extend our repair pipelining to a very general case in which we use a weighted path selection to try to select the best path of helpers for the repair. So let's take a look at the first case. The cyclic version works as follows. Basically, the idea is we divide the repair of the block into groups. Each group is to repair multiple slices. And we do it in a cyclic manner. So N1 send data to N2, N3, and N4. N2 also send data to N3, N4, and N5. And then N1 back to N1, and N3 to N4 back to N1 and N2. Then N4, N1, and N2 will send to the requester. And then we repeat these repair operations for another group. So we can see that right now the requester can receive the repair data from k-1 helpers, as opposed to the previous basic case, we only receive from one helper. And if we show that if we consider again the homogeneous environments, we can also show that the cyclic version still maintain the one-time slot property for the repair time. And for the weighted path selections, basically the main idea is to find a path of k+1 nodes that minimizes the maximum link weight, while we associate the link weight as, for example, the inverse of the link bandwidth, and any straggler could be associated with large weight. So we assume that we can do some measurements to collect the weight information. And then we try to find the best path. Now, if we do the brute force search, that would be very expensive. There will be a lot of permutations. So what we propose an algorithm that still maintains the optimality, that's still able to find the minimum of the maximum weight path. However, we can prune away the path that we know that must be non-optimal. Basically, the idea is if we know that a link has weight larger than the maximum weight of the currently optimal path, then I don't need to consider any path that containing error, because I know that they must be suboptimal. So our algorithm can significantly reduce the search time while it's still optimal. So if we want to implement this idea in distributed storage system, that could be quite difficult because different storage systems have their own way to do the erasure coding. So we propose a easy pipe system. Basically, it's a middleware that could be integrated on top of the existing distributed storage system. So the main idea is we can intercept the repair operations in the underlying distributed storage systems, and allow the helper, which we implement as daemon, to directly read the local blocks via the existing local file system. And the coordinator will maintain the block locations and block to stripe mappings. And we find that this type of implementation can be applied to HDFS and QFS. And when we do the integration, we find that we only need less than 200 lines of code changes to the existing storage system. ECPipe itself has around 3,000 lines of code. So we move the repair logic to ECPipe while minimizing the code changes to existing storage systems. So I will highlight some evaluation results. First is about the ECPipe performance on a 1 gigabit cluster. So the x-axis is the slice size, y-axis is the repair time. So basically, if we reduce the slice size, we have more slices. So theoretically, we can improve the repair performance. However, if we make a slice too small, that will have a lot of transmission overhead, because basically you have to transmit one slice at a time to the next helper. However, if it's too large, then there will be less parallelization. So the best slice that we found will be around 32 kilobytes. And we find that the repair pipelining performance will be achieved up to significantly reduce the repair time by up to 90%. And we also compare this with the direct send time, meaning that you just transmit one block over a link, and we find that it only has 7% more overhead over the 1 gigabit length, and it also conforms to our theoretical guarantees that is about 0.1 repair time. We also consider the full node recovery performance. X-axis is the number of requesters, y-axis is the recovery rate, and again, the result is similar, and we find that actually, although if you increase the number of requesters, you can improve the recovery rate. However, repair pipelining still gives you the benefit. And if we use our greedy scheduling, you can improve the performance than just simply randomly choose the helpers for doing the repair. We also do the experiments on Amazon EC2. Left side is about the evaluation on North American cluster, and right side is about on the Asia cluster. And we also see similar performance gain. I won't go into the details here. And finally, we show the repair performance on HDFS and QFS. And our finding is, again, ECPipe can significantly improve the repair performance. And we find that actually the conventional repair under ECPipe can outperform the original conventional repair inside the distributed file system. So if you use conventional repair itself with the ECPipe, it still gives you the performance gain because it avoids fetching blocks from the distributed storage system routine. However, I'd like to emphasize that the performance gain is still due to repair pipelining. So to conclude, we propose repair pipelining as a general technique for fast repair in erasure coded storage. And we publicize our source code, so you can take a look at our source code and see what we do. Thank you, and I appreciate your comments and questions.
Hi, this is Atish Katpal from NetApp. So your talk focused mainly on recovery of single node failures or single block erasures. I was just curious that what are the implications if there were more than one node failures in your system?
So in that case, we will assume we use the conventional repair. However, in the field studies, it shows that more than 98% is about single block repair. So in this case, we only focus on optimizing that one.
So the pipeline-based recovery mechanism is not going to be able to recover more than one failure. That's what you're saying?
Yes. So if that case, we will resort to the conventional repair.
Okay, and the other question I had was that, in the beginning of the talk, you mentioned that there are different kind of codes, like regenerating codes. Some of them are, minimal bandwidth, repair bandwidth codes, and some of them are minimal storage regeneration codes. So I was curious that in your case, the amount of bandwidth that you end up using overall in the network is same as, regular RS codes.
Right,
is that
that's
right?
Right, that's okay. Right. We still retrieve K blocks. However, if we apply this to the repair optimal codes, we also show in our experiments, we construct K blocks, we compare with those codes that read less than K blocks, but they may not be able to fully utilize the bandwidth, and we still show the performance gain. However, the amount of traffic is still K blocks.
Right, and one last question. I was wondering if you've tried to see if similar pipelining mechanisms can actually be applied to these regenerating codes. Any thoughts on that?
We apply this to regenerating code, but in regenerating code, we still read from K blocks. So one open question is, how do we apply repair pipelining while still minimizing the repair traffic? That's the open question.
Okay, thank you.
Thank you.
Okay, so my name is Muryong Ra from AT&T Labs. So good presentation, thank you. And I have two questions. So in terms of performance, you gain 80% more than PPR. So PPR is in some sense pipelining the operations as well, right?
Yes.
So what is the intuition, that your scheme is 80% better than?
Yep.
What is the setup?
Okay.
basically?
Intuitively, our main idea is to slice a block.
Right.
So just because of slicing a block, we can just make it more fine-grained and try to fully utilize the bandwidth. Now, in our example, we use k equals to 10. And so in PPR, that would be like 5 times loss, log 10. And our case is 1 times loss. So you can see why there's an 80% performance. Theoretically, that also conforms to our experimental results.
Okay, so
Thanks.
second question is, in your implementation, you introduced the middleware, right? Which is separate from the original I/O path, data path, right?
Right.
So if there is a client I/O going on at the same time, will there be any problem? Have you thought about that?
Well, the thing is, after we do the repair, clients still can issue the same read-write request through the original I/O path because the data is still there, and we make sure that the metadata is still intact. However, when you say while we do the repair and then the client issue the request, we didn't consider that case, but we believe that that should be solvable. I think it's an engineering problem.
Right. Okay.
Thank you.
Thank you.
Yes.
Hi, Keith Smith, also from NetApp. I actually wanted to follow up on Atisha's question. You said that if there's multiple failures, you fall back on doing repair the traditional way.
Yeah.
And I was confused. Is that simply what you do in the EC pipe implementation? Or is there something fundamental about this idea of slicing blocks up and pipelining them from one place to another that doesn't work if you have to repair more than one block?
I think we just don't consider that.
Okay.
I think because we basically find K helpers. So even if there are multiple failures, it's just, you can still find the K helpers and do the repair pipelining. But the thing is, we don't do any evaluation, so
I understand that you haven't done it in your prototype. I wanted to understand conceptually whether there was a problem.
You're right.
Okay.
Thank you.
Thank you.
Thank you.